push that rock, and some math. Let's talk about the differentials. Leibniz notation gives us two differentials. dy is the differential of y, and dx is the differential of x. Now, I like Euler's notation. When I'm given a function, I think it's super convenient just to say y prime equals 3x squared and let this prime symbol represent derivative. I also like Euler's other notation for when you're treating differentiation like an operator, like I'm operating on this function. So I have 2x plus 5 to the 12th. So, whoa, messed that up. Let's say 2 times 12 is going to be 48. So you bring the 12 out front, you subtract 1, and then don't forget to multiply by the derivative of the inside by chain rule. And so I get the derivative. So I like this notation. I use it a lot, as you've been noticing. I like this, but there is a reason why Leibniz notation is genius. It is genius. So the Leibniz notation, instead of using y prime, we like here I did the power of 3x squared, but we did dy dx, and this has actually got a lot of genius to it, and I'm going to try to explain why. So let's look at a curve of some function f of x. And let's think about the tangent line at A. Now, if what we think about is a little nudge over from A, so we'll call this little change right here the change in x. And it turns out that you can think of dx as that change in x. The differential of x is the change in x. And of course, that creates a change in y, unless it's a constant function. And so then we have a slope, a rise and a run, but this change in y would give us the wrong slope for the slope at this point, right? That would be the slope of the secant. That we could get the slope of the secant, but the slope of the secant is not going to be equal to the slope of the tangent because this doesn't have a constant slope like a typical line. So the thing about the differential of y is it's going to be close to the change in y as long as the change in x is tiny, but there is a slight difference. And the change in y is that given by the tangent line, because the tangent line has the slope of the curve at this point. Okay, so this distance here is the differential of y. Now, how can I compute the differential of y? Well, it's quite easy. You just multiply the slope by the change in x, and that's where Leibniz's notation comes in. So to do Leibniz notation, I say dy dx is equal to 3x squared, and this is a formula for the slope. And this is our change in x. So since Leibniz recognized there's two different quantities going around, he decided to use a fraction as his symbol for the derivative. And then he's going to do something very weird and multiply by part of his derivative symbol. And he can do that because the derivative actually involves two changing quantities. So it turns out to work out, and this is how you would get the differential of y. And so if you want to know the differential of y at some given x value, for some given change in x, you just plug in the given x value and the given change in x, and you'll have the differential of y, which will be super close to the actual change in y that's associated with the change in x. Anyway, this is the differential of y. In general, it is the derivative. See, that was the derivative of the given function times dx. There is the general formula for the differential of y. Math made simple. Simpson math.